Welcome back to video lecture on gas dynamics and jet propulsion, Unit 5, space propulsion. It is a third video. Here, the topic name is back pressure and optimal expansion. For optimal performance, the pressure of the gas at the end of the nozzle should just equal to ambient pressure. If the exhaust pressure is lower than ambient pressure, then the vehicle will be slowed by the difference in pressure between the top of the engine and the exhaust. On the other hand, if the exhaust pressure is higher, then exhaust pressure that would have been converted into thrust is not converted and the energy is wasted. To maintain this ideal of equality between the exhaust exit pressure and ambient pressure, the diameter of the nozzle would need to increase with altitude, giving the pressure a longer nozzle to act on. This increase is difficult to arrange in a lightweight fashion, although is routinely done with other format of jet engine. In rocketry, a lightweight compromise nozzle is generally used and some reduction in atmospheric performance occurs when used at other than design altitude or when throttled. To improve on this, various exotic nozzle design such as the pulse nozzle, stepped nozzle, the expanding nozzle, and the aerospike have been proposed, each providing some way to adapt to changing ambient air pressure and each allowing the gas to expand further against the nozzle, giving the extra thrust at a higher altitude. When exhausting into sufficiently low ambient pressure, several issues arise. On this, the sheer weight of the nozzle beyond a certain point for a particular vehicle, the extra weight of the nozzle outweighs any performance gain. Secondly, as the exhaust gases addiabatically expand within the nozzle, they cool and eventually some of the chemical can freeze, producing snow within the jet. This causes instability in the jet and must be avoided. On a D-level nozzle, the exhaust gas flow detachment will occur in a grossly overexpanded nozzle, as the detachment point will not be uniform around the axis of the engine. A side force may be imparted to the engine. This side force may change over time and result in control problem with the launch vehicle. Thrust vectoring. Many engines require the overall thrust to change the direction over the length of the band. A number of different ways to achieve this have been flown. The entire engine is mounted on a hinge or gimbal and any propellant feed reaches the engine via low pressure flexible pipes or rotary coupling. Thus the combustion chamber and the nozzle is inbuilt. The pump are fixed and high pressure feeds attached to the engine. Multiple engines are deployed but throttle to give the overall vector that is ensured, giving only a very small penalty. Fixed engine with a vernier thruster high temperature vanes held in the exhaust that can be tilted to deflect the jet. Overall rocket engine performance. Rocket technology can combine very high thrust, very high exhaust speed, around 10 times the speed of sound in air at sea level, and a very high thrust or bar weight ratio greater than 100, simultaneously, as well as being able to operate outside the atmosphere and while permitting the use of the low pressure and against the lightweight tank and structure. Rocket can further optimize to even more extreme performance along one or more of these axes at the expense of the others. Specific impulse. The most important metric for the efficiency of a rocket engine is impulse per unit of the propellant. This is called a specific impulse, usually written ISP. This is either measured as a speed, the effective exhaust velocity VE in the meter per second or FT per second or as time seconds, An engine that gives a large specific impulse is normally highly desirable. The specific impulse that can be achieved is primarily a function of the propellant mix and ultimately would limit the specific impulse, but practical limits on the chemical chamber pressure and the nozzle expansion ratio reduce the performance that can be achieved. Space flight. Space flight is the act of traveling into or through outer space. Space flight can occur with a spacecraft which may or may not have humans on board. Examples of human space flight include the Russian Soyuz program, the US Space Shuttle program, as well as the ongoing International Space Station. Examples of manned space flights include space probes which have Earth orbit, as well as satellite in orbit around Earth, such as communication satellites. Space flight. Space flight is used in space exploration and also in commercial activities like space tourism and satellite telecommunication. Additional non-commercial use of the space flight include space observatories, reconnaissance satellite, and other Earth observation satellites. A spaceflight typically begins with a rocket launch, which provides the initial thrust to overcome the force of the gravity and propels the spacecraft from the surface of the Earth. Once in space, the motion of a spacecraft, both when unpropelled and when under propulsion, is covered by the area of the study called astrodynamics. Some spacecraft remain in space indefinitely, some disintegrate during atmospheric re-entry, and others reach a planetary or lunar surface for landing or impact. Types of spaceflight. Human spaceflight. The first human spaceflight was Vostok 1 on April 12, 1961, on which astronaut Yuri Gagarin of the USSR made one orbit around the Earth. In official Soviet document, there is no mention of the fact that Gagarin parachuted the final several miles. The international rule for aviation records state that the pilot remain in his craft from launch to landing. This rule, if applied, would have disqualified Gagarin's spaceflight. Currently, the only spacecraft regularly used for human spaceflight are Russian, Soviet spacecraft and the US Space Shuttle fleet. Each of those space programs have used other spacecraft in the past. Recently, the Chinese Sunquan spacecraft has been used 3 times for human spaceflight and a spaceship twice. Suborbital space flight. On a suborbital space flight, in the spacecraft reaches space and then return to the atmosphere after following a ballistic trajectory. This is usually because of insufficient specific orbital energy, in which case a suborbital flight will last only a few minutes. But it is also possible for an object with enough energy for an orbit to have a trajectory that intersects the Earth atmosphere, sometimes after many hours. Pioneer 1 was NASA's first space probe intended to reach the Moon. A partial failure caused it to instead follow a suborbital trajectory to an altitude of 113,854 km, and before the re-entering the Earth atmosphere 43 hours after launch. The most generally recognized boundary of space is the Garmin line, 100 km above the sea level. It is not generally recognized by the public that the increase in potential energy required to cross the Garmin line is only about 3% of the total orbital energy required by a lowest possible Earth orbit. In other words, it is far easier to reach space than to stay here. On May 17, 2004, civilian space exploration team launched the GoFast rocket on suborbital flight, the first amateur spaceflight on June 24, 2004. Spaceship One was used for the first privately funded human spaceflight. Orbital spaceflight. A minimal orbital spaceflight required much higher velocity than a minimal suborbital flight, and so it is technologically much more challenging to achieve. To achieve orbital spaceflight, the tangential velocity around the Earth is important as altitude. In order to perform a stable and lasting the flight in space, the spacecraft must reach a minimal orbital speed required for a closed orbit. Interplanetary spaceflight. An artist's imaginative impression of a vehicle entering a half-fold for interstellar travel. Interplanetary travel is travel between planets within single planetary system. In practice, the use of the term is confined to travel between the planets of the solar system. Interstellar spacecraft are currently leaving the solar system on escape trajectories. The one farthest from the Voyager 1, which is more than 100 AU distance and is moving at 3.6 AU per year. In comparison, Proxima Centauri, the closest star other than the Sun, is 267 to 260,000 AU distance. It will take Voyager 1 over 74,000 years to reach this distance. Vehicle design using other technologies such as nuclear pulse propulsion are likely to be able to reach the nearest the star significantly faster. Another possibility that would allow for human interstellar spaceflight is to make use of time dilation, as this would make it possible for passengers in a fast-moving vehicle to travel further while again very little. In that, their great speed slow down the rate of the passage of the onboard time. However, attaining such high speed would still require the use of some new advanced method of propulsion. Intergalactic spacecraft. Intergalactic travel involves spaceflight between galaxies and is considered much more technologically demanding than even interstellar travel, and by current engineering terms is considered science fiction. Effective speed ratio between flight speed to the jet velocity divided by sigma is equal to sigma u divided by cj. We know that thrust F equal to ma cj minus u. Next one, specific thrust. Specific thrust equal to ratio between thrust divided by mass flow rate. Thrust specific consumption ratio between mass of the fuel consumption per thrust propulsive force. Specific impulse equal to thrust developed per unit weight flow rate. Next one, propulsive efficiency. Propulsive efficiency is the ratio between propulsive power or thrust power to the power output of the engine. Next one, thermal efficiency. Thermal efficiency ratio between power output of the engine to power input to the engine through the fuel. Next one, overall efficiency. It is the product of propulsive efficiency and thermal efficiency, or propulsive power thrust power to the power input to the engine. The first problem. A rocket moves with a velocity 10,000 km per hour with an effective exhaust velocity of 1,400 meters per second. The propellant flow rate is 5 kg per second, and the propellant mixture gas a heating value of 6,500 kJ per kg. Find propulsive efficiency, engine output, thermal efficiency, overall efficiency. We know that rocket speed U equal to 2,777.7 meter per second. Jet velocity 1,400 meters per second. Calorific value, propellant mass flow rate. Therefore, we get the sigma effective speed ratio 1.984. Therefore, we get the propulsive efficiency equal to 80.4%. Thrust 7,000 Newton. Therefore, propulsive power 19.44 megawatt. Then propulsive efficiency. From the propulsive efficiency, we get the engine output 24.18 megawatt. then thermal efficiency equal to 73.3%, and finally overall efficiency equal to 58.9%. So the next are the tutorial problems. Thank you.